All right, let's get started. So welcome to our presentation of Seamless. We are a team of three. I'm Ethan Weiner. I'm here with my teammates, Ryan DeJonghe and Jason Wang. So first off, what is Seamless? Seamless is an open source CI/CD tool that streamlines the deployment of containerized microservice applications. But before we actually get into just what that means, let's start off with an agenda. So we'll split up the presentation into two sections. In the problem domain section, we'll talk about what deployment processes are, and then we'll introduce CI/CD and discuss an important trade-off within the world of CI/CD. We'll also go into the specific challenges of CI/CD pipelines for microservices specifically. And then we'll look into some existing CI/CD tools. In the second section, we'll introduce Seamless, taking a tour of its core infrastructure and looking at the tasks that it actually runs and how it enables users to monitor their pipeline. And finally, we'll just talk a bit about how we built Seamless for performance and scale. But first off, what is a deployment process? So a deployment process is all the steps involved in getting new code from a developer's machine to a production environment. Most deployment processes tend to follow the same rough outline of stages. So let's take a look at what we're calling the 4 core stages of a deployment process. First off, we have the source stage. For any deployment, the source of the code must be identified. And usually it's a version control system like GitHub that's used to collect code from local developers in one central place. And this is where the deployment process begins. Next, the test stage runs tests on the code to ensure quality and functionality. During the build stage, the updated source code is packaged with its dependencies into a single deployable artifact. And finally, during the deploy stage, the built artifact is actually shipped off to a production environment accessible to end users. So to recap, there are 4 main stages of a deployment process: source, test, build, and deploy. Now that we've talked about what a deployment process is, let's talk about the 2 types of a deployment process: manual and automated. Traditionally, humans would manually perform most stages of a deployment process, whether that may be running commands or navigating an interface. Now, most deployment pipelines are automated to some degree. And whether a deployment process is manual or automated can pretty much affect 2 major aspects of deployment. The first is the speed with which new code can be delivered to end users. The second is reliability, which refers to the assurance that only high-quality functional code is released to end users. Let's talk about speed first. With manual deployments, when a developer makes a change, they often need to wait for another developer, maintainer, or operations staff member to actually go ahead and begin the manual deployment process. On the other hand, automated deployments are triggered immediately upon updates in version control. And even once the deployment process starts, manual deployment processes experience delays between steps themselves. This effect is amplified further if those different steps are being carried out by different teams that must coordinate to carry everything out in the correct sequence. However, in an automated deployment process, when one step finishes, the next one usually starts immediately. Okay, so we've discussed how manual deployments are slower than automated ones. Now, let's talk about reliability, which means the confidence companies can have that the code they're releasing into production will actually work in production. As we'll see in a moment, manual deployments are usually less reliable than automated ones. So first of all, manual deployments can run into environmental inconsistency issues. What this means is that a developer's local environment is probably not going to be configured identically to the production environment to which it will be deployed. The environments could have, say, different operating systems, maybe different dependencies installed with different versions, different environment variables. You get the idea. As a result, code functioning in a developer's local environment doesn't necessarily indicate that it will also function properly in production. But with manual deployments, developers or operation staff often push straight from their local machines to production. Automated deployment pipelines address this issue. Instead of humans running tasks and deploying from their own machines, automated deployments use a centralized build server to automatically run all tasks in a consistent environment on every deployment. The build server is kind of like a gate. If the build or test fails on the build server, the code won't make it to production. Another reason for these differences in reliability is that each step in a deployment process is really just a set of rote activities, like running commands, clicking through an interface, or maybe adjusting configuration files. Build servers, of course, are machines, which makes them better than humans at performing these kind of rote activities in a consistent and reliable manner. For example, like a developer might forget to run a few tests, but a build server, assuming it's configured properly, probably won't. Okay. To recap, manual deployments tend to be slower and less reliable than automated deployment pipelines. However, as we'll see in a moment, there are some caveats to that. So we've talked about what deployment processes are and why the industry has shifted toward automated ones. Now let's talk a bit about a particular trade-off most automated deployment processes need to make. We mentioned that automated deployments are safer and faster than manual ones, but it's actually always as simple as that. For companies used to a manual deployment process, switching immediately to a fully automated pipeline can be risky. For example, if the company maybe lacks a comprehensive test suite. So actually retaining some aspects of traditional manual deployments in an automated deployment pipeline can make them safer for some companies. Safe, meaning decreasing the likelihood of bugs entering production. In order for a team to dial the degree of automation in their deployment pipeline to their safety and velocity needs, there are a few key decisions they can make. These decisions are closely related to a set of combined practices called CI/CD, which stands for continuous integration and continuous delivery for deployment. Let's break these down a bit further and see how each can be used to achieve different goals in terms of safety and in terms of speed. So continuous integration is the practice of regularly merging code into the main branch of a central repository after it's built and tested. Continuous integration is mainly focused on version control, the goal being to quickly get developers' code into the main branch. Now, how continuous a team's continuous integration practices depends largely on their merging strategy. Teams can have workflows that either automate the merging of branches or pull requests, say when they pass status checks, or they can require a manual review process by a team member before merging. Although automating merging can speed up the pipeline, it might introduce the risk of potentially merging code that hasn't really undergone adequate testing and review. All right, now let's talk about continuous delivery. Continuous delivery extends upon continuous integration by regularly taking the new build and promoting it to a staging environment where it is held for manual approval. This effectively prepares the new version for release without actually going ahead and releasing it. But with continuous deployment, the new version isn't just prepared for release. It is immediately released into production. The main takeaway from the previous few sections is that companies can enhance safety of their CI/CD pipeline by mandating human code reviews before merging, and also by using a staging environment. Alternatively, they can enhance the velocity of their pipeline by automating merging and continuously deploying. So far, we've talked about deployment processes, what CI/CD is, and how CI/CD pipelines can be adapted to meet these different speed and safety goals. Now let's talk about how they can be adapted for two different application architectures, monoliths and microservices. But first of all, let's actually define the terms monolith and microservice. A monolith is a single unit, a single code base. All of its components exist within the scope of one application. A microservices architecture, on the other hand, consists of more independent, loosely coupled applications that are distributed across the network. One significant way in which these two architectures differ is in how they are deployed. For a monolith, since it's just one application, that entire application must be restarted whenever it is deployed. As a result, a monolith always has to be deployed all at once. But microservices, on the other hand, are split into multiple applications, so they can be deployed as smaller, independent units. This also means that each microservice can be deployed on its own schedule. This independence of deployments is actually one of the prized characteristics of microservices. However, as Ryan will show in a second, this exact feature of microservices actually introduces a new challenge when it comes to managing their CI/CD pipelines.
Thanks, Ethan. Two challenges we identified in our research of CI/CD pipelines for microservices were the management of deployment pipelines and comprehensively testing microservices in the pipeline. Let's start with the challenge of pipeline management. One way to deploy microservices is to attach an individual CI/CD pipeline to each one. This many pipeline approach gives teams full control over the pipeline and its steps. It can be used by applications with independent microservices managed by autonomous teams. However, for organizations that are smaller or have more centralized management, it can be a nightmare to maintain tens or hundreds of individual pipelines along with their configuration files. Sharing and reusing pipeline steps can eliminate redundancies across pipelines, but this approach has its own downsides. We still have to manage multiple pipelines as well as the shared steps. The two previous approaches assume that each microservice must have its own dedicated CI/CD pipeline. But what if we create a single, reusable pipeline? When starting a run, each service passes its own parameters, such as test commands and trigger type. Adding a new microservice to the pipeline is simply a matter of providing these parameters. This approach can make it simpler to build and maintain pipelines. Another challenge with deploying microservices has to do with their unique testing requirements. Testing microservices can be challenging due to their distributed nature. They need to be tested both for their own internal functionality and for how they interact with other microservices. We will now look at three approaches used to test microservice applications: unit testing, integration testing, and the use of staging environments. Unit testing involves testing components within a single service. In the diagram, service A is tested internally to verify that it works properly in isolation. Testing does not pass outside the boundary of service A. Integration testing involves making network calls to test multiple services together as a single subsystem. This verifies that when a service is updated, it continues to interact properly with other services. Lastly, staging environments replicate production conditions and include all the microservices in the system. This can be used to test and inspect the whole system as if it were in production. So to recap, two microservice-specific CI/CD challenges are managing pipelines and testing them extensively. At this point, we have introduced deployment processes and CI/CD, as well as some of the difficulties that come when using CI/CD with microservice applications. Next, we will look at some of the existing CI/CD solutions available and how Seamless compares to these. Open source DIY tools may be useful for organizations that require extensive pipeline customization. Tools like Jenkins and GitLab allow for pipeline reusability, but implementing them can be challenging because they typically require knowledge of plugins and integrations. Commercial solutions like CodeFresh and CircleCI may not always be as flexible as open source tools, but do generally provide some customization capabilities. They are usually easy to use, and like DIY tools, they offer reusable pipelines. After exploring the existing solution space, we felt there was room for a tool that was both open source and easy to use. With Seamless, we wanted to build a tool for a specific user, companies with fewer employees that have difficulties managing CI/CD pipelines for multiple microservices. They are seeking an easy-to-use solution that is open source and provides the ability to reuse a single pipeline. We will now take a closer look at Seamless. Seamless is a CI/CD pipeline designed for containerized microservices deployed to AWS's Elastic Container Service, specifically ECS Fargate. Seamless uses a standard set of pipeline stages, which makes it easy to use right out of the box, and it offers some customization of the workflow. It provides options for testing microservices in isolation and together. It also features pipeline monitoring and notifications. In the following sections, we will explore the steps a user takes to install, set up, and run Seamless. First, the user installs the Seamless npm package globally. Next, in the CLI, the user runs Seamless init followed by Seamless deploy to provision infrastructure on AWS. After this completes, the user can access the Seamless dashboard. To set up a pipeline, the user provides ECS cluster names for production and staging environments. They can then continue to set up a service. Here, the user can connect a service to the pipeline. Under triggers, they can specify which GitHub events will start the pipeline. In the next section, they can decide whether to automatically merge pull requests, use a staging environment, or auto-deploy to production. The user can also provide the repository URL, test commands, and other options. After a service has been set up, the user will be able to monitor pipeline run progress. The pipeline run is in progress, and the user can stop or rerun it at any time. The run header shows the runtime and duration, as well as the git commit data. Beneath the run header, the details of all pipeline stages are displayed. Their statuses are updated in near real time, so the user can know exactly when one stage completes and the next stage begins. Lastly, the user can inspect each stage's logs in order to monitor its progress. If a stage fails, these logs can help with troubleshooting. Putting it all together, the Seamless dashboard enables the user to monitor run status and run times, as well as stage status and logs. Next, we will consider 4 primary challenges we faced when building the core pipeline. First, we needed to determine how to model and store pipeline data. Next, we investigated how to automatically trigger the pipeline when specific events occur. Then we had to find a way to manage pipeline tasks. And finally, we needed a way to figure out how to perform these tasks. Now we'll give a brief overview of the architecture we used to address these challenges, and afterward, we will look at them in more detail. We started by creating the data model and selecting a suitable database. Then we set up a backend server to handle requests and communicate with the database. Next, we built the components to automatically trigger the pipeline. When the user updates their code repository, GitHub sends a webhook to our backend server. The backend server processes the webhook and retrieves data for the service associated with the repository. With this data, it then instructs the task manager to start the pipeline. The task manager orchestrates the cloning, testing, and building of the updated code as it progresses through the pipeline. The actual work of performing all tasks is done by the task executors. Together, the manager and the executors form the heart of the pipeline. The final task performed is deployment to the production environment. This diagram reflects the core architecture of Seamless's deployment process, from the moment a user pushes a code change when it is released into production. Next, Jason will present the challenges and infrastructure in more detail.
Thanks, Ryan. I'll begin this section by talking about the data model. With Seamless, we can use a single pipeline for multiple services. The data model reflects this by using several one-to-many relationships. Each service can be run many times, and each run has many stages. For the database, we chose Postgres on Amazon RDS, and also used the Prisma ORM for schema updates. With that in place, the next step was to automate the pipeline. One of the key features of Seamless is that the pipeline automatically starts whenever there's a code update. To make this happen, we use webhooks. Let me walk you through how that works. First, we create a webhook in the repository using the OctoKit library. Once that's set up, GitHub will let us know of any code updates. Then, when the user makes an update to the code, GitHub sends us a webhook, which is a post request with details about the update, such as the commit message and the hash. Finally, the backend processes the webhook and starts the pipeline. So when the pipeline starts, it needs to coordinate and execute a series of tasks. To handle this workflow, we needed to find an infrastructure component to serve as a task manager. At first, we tried a job queue, and it worked well for linear workflows. However, as the workflows became more complex, the job queue just wasn't flexible enough for what we wanted it to do. We needed something that can handle conditional logic, like whether to use a staging environment or not. We also needed a way to track the state of the entire pipeline. So after looking into a few options, we decided that the task manager should be implemented as a state machine, which is a model of how a system behaves. You can think of it as a flowchart from how to get from start to end. And if we want to use this to model a system, we have to map out all the possible states, as well as the conditions for moving between the states. And sometimes we need to make decisions, which determine the direction that we go into next. Now that we understand what state machines are, let's see how we can use them to model a CI/CD pipeline. So this is our pipeline implemented as a state machine. Like the previous diagram, it transitions through multiple states between start and end. The source, test, build, and deploy stages are the same ones we talked about earlier. And in the middle of this diagram, it shows two decisions we have to make, which are whether to use a staging environment and whether to approve staging after we've reviewed it. So in order to turn this state machine into infrastructure, we used an AWS service called step functions. And just as a reminder, this state machine is a task manager. It doesn't actually perform the tasks themselves. Its job is just to trigger the tasks and wait until they're done so that it can move on. So where are these tasks actually performed? Well, that's the job of the task executors. And to better understand what they do, let's first go over what a task is. In Seamless, a task is a JavaScript program. We use Execa, which is a package for running shell commands. We also use the AWS SDK to interact with infrastructure. For example, during the build task, we use Execa to build a Docker image. And in the deploy task, we use the SDK to launch that image into production. Now that you know that tasks are JavaScript programs, we can now talk about the infrastructure for running them. We looked at two options, containers and virtual machines. Our initial idea was just to run everything on a virtual machine, but after more research, we decided to go with containers because they're more lightweight and faster to spin up. This is because unlike virtual machines, they don't include a guest OS, which can take up a lot of space. And the reason why fast spin-up time was so important to us is because different teams have different commit frequencies. So we wanted to support a variety of usage patterns. After settling on using containers, our next step was to figure out how to manage containers on AWS. So on the top here is our task manager, which needs to execute some tasks in AWS. There are two services that can do this for us, ECS on EC2 and ECS Fargate. Both of them can run containers, but the main difference is who manages the virtual machines where the containers are placed. With ECS on EC2, the user has more control, but with Fargate, AWS does all the management. For our case, the deciding factor was that we actually needed that additional control. Some of our tasks run Docker commands inside of Docker containers, and we achieved this by having access to the host machines. Therefore, we chose ECS on EC2 for executing tasks. Now, if you take a look at the bottom there, you can see that all the tasks are running by themselves. However, a pipeline is a series of connected steps, and it's important for the tasks to be able to share data with each other. And that was the next challenge we had to tackle. As the pipeline runs, some tasks depend on the output from previous ones. For example, in the source stage, we clone the code. And in the test stage, we run tests on that same code. To avoid cloning twice, we store the data in a central location so that all tasks can access it. We decided to create a shared Docker volume on the AWS Elastic File System, or EFS. It can connect to any number of virtual machines or containers. It also scales automatically, so we don't need to set capacity in advance. Now, one problem with a shared file system is naming conflicts. If the pipeline multiple times, data could be overwritten when cloning the source code. And to prevent this, we organize the data by commit hash, which means that each version of the code gets its own folder. And another benefit of doing this is that it enables parallel execution, meaning multiple pipelines can run simultaneously and write to the same file system without conflicts. This is a critical feature for scaling, which we will talk about later. As an alternative to EFS, we also considered AWS Elastic Block Storage. Although it would have offered higher performance, it's only designed to be mounted to just a few EC2 instances. In comparison, EFS can mount to many instances and containers, which made it the better choice for our use case. Let's take a moment to step back and see how this core architecture solves the 4 challenges that we talked about earlier. First, we created the data model and set up a Postgres database. Next, GitHub sends a webhook, which auto-triggers the pipeline. Then we use step functions to manage the tasks, and they're executed using ECS and also use EFS to share data. Finally, the new code is deployed to production. Now that we've covered the core pipeline infrastructure, we'd like to explain how some of the tasks were implemented. And here's the full list of all the pipeline tasks that Seamless performs. First, we clone the code. Then we run quality checks and unit tests. After building the Docker image, we have the option of running integration tests. And finally, we deploy to staging and production. And if something goes wrong, we can perform a rollback. Next, we'll take a closer look at two of these, integration tests and rollbacks. So the goal of integration testing is to make sure that multiple microservices are working correctly together. We'll review two ways of doing that and which of those Seamless uses. Let's say we just updated service A, which is shown in green here, and we need to test it with services B and C. With this first approach to integration testing, we test service A against live production instances of B and C. This is convenient and simulates a real-world scenario, but it's also risky. Any destructive calls we make could unintentionally impact the production system. So the second approach is just to avoid production altogether. We spin up A, B, and C in an isolated test environment and do all of our testing there. While this does add complexity and requires additional resources, it eliminates the risk of impacting production. And because of this safety benefit, Seamless uses this second approach. So to make all this work, we use Docker Compose, which is a service for container management and networking. Users provide a configuration file that specifies the dependencies for service A. In this example, that's B and C, which Docker Compose pulls from a container registry. And when all the services are running, we can execute the integration tests. After integration tests pass and we deploy the updated service, if we still find issues in production, we need a way to revert to a previous version. And that's where rollbacks come in. If you recall, earlier we talked about the safety velocity trade-off. Using CI/CD can help us move fast, but when we do, it might be easier for bugs to creep into production. So we need a rollback feature for restoring service if something breaks. As shown on the left here, Seamless can retrieve a list of all the document images the user has deployed. And if we find a bug in production, we can hit the rollback button and revert to a previous stable version, which is then redeployed. As part of the process, the buggy version is removed. In order for rollbacks to work, we tag each Docker image with the git commit hash. Here in the UI, you can see a list of available rollback images for this service. Each service can be rolled back individually without impacting other services in the system. So we just covered how rollbacks help when there are bugs after deployment. We also want to catch issues and alert users before deployment. That's why if any tests fail, Seamless won't deploy that code to production. And to keep track of those test failures and other problems, we built some monitoring features. We set up a dashboard for status updates, a logging service, and a notification service. Here's the dashboard, which we saw earlier. As you can see under the pipeline and stage headings, statuses start at in progress and are automatically updated to either success or failure. Status updates are also sent as user notifications via email, Slack, and PagerDuty. Both the logs and the statuses are received from the backend using WebSockets. So next, let's take a closer look at that logging service. When it comes to troubleshooting deployments, having a real-time log feed is really useful. That's why we use the WebSocket API to connect the dashboard to the backend. This lets the user see updates in near real time. As for backend log processing, we wrote a JavaScript package, which is used by all the tasks. This allowed us to fully customize the log payloads and also have more control over where the logs were stored. Since we needed to quickly store and retrieve large volumes of logs, we used a Redis cache. The logs are only kept for 48 hours because they lose relevance after a while. Now that we've covered pipeline monitoring with a dashboard and the logging service, let's look at some of the scaling optimizations. We designed our infrastructure to accommodate a high volume of pipeline runs. If a user is making frequent commits or adding microservices, the infrastructure must be able to support multiple runs in parallel. We handle this by launching new instances of AWS step function for each pipeline run. This diagram shows the pipeline being triggered by different services at different times and multiple runs occurring simultaneously. The next improvement we made was to scale the backend server. The backend is a containerized express server. When load is low, a single container might work just fine. But when the application grows and we have more and more pipelines running, it could get overwhelmed. So we decided to use Fargate and a load balancer. This means that when load increases, Fargate will spin up as many containers as needed, automatically scaling to meet demand and distributing traffic with a load balancer. This enables the backend to handle high load. And that is the last feature we're going to cover today. Now, to bring everything together, Ethan is going to present the final seamless architecture.
All right, let's start with the flow from source to production. And we'll begin from the top left. So first of all, whenever code is updated, GitHub sends a webhook to the backend, which is an express server running on Fargate. The backend then retrieves the pipeline data that it needs from a Postgres database. It sends this data to the task manager, which is a state machine that's implemented using step functions. Now, the state machine actually executes each of the pipeline tasks in its own container using ECS on EC2. And all these containers share data with EFS. Finally, the updated service is deployed to staging and production Fargate clusters. Now, let's highlight some of our monitoring features. During the pipeline run, Task Manager sends notifications through SNS. The logs from the task containers are stored in Elasticache Redis. And finally, all status updates and logs are sent to the dashboard through the WebSockets API gateway. Currently, Seamless is a CI/CD pipeline for a niche use case, specifically node-based containerized microservices that deploy to ECS Fargate. Now, we've identified several areas that could maybe improve in the future in order to support more use cases and functionality. In particular, we'd like to add some more testing options, support more deployment options, support additional runtimes, and also cache dependencies between pipeline executions to help speed up the pipeline. And this concludes our presentation. Thanks for attending, and now we'd be happy to answer any questions.
So the first question, and this is probably one we can all take. When what were the highlights of working on Seamless? And maybe Jason or Ethan can start.
Yeah, I can give that a go. Highlights of working on Seamless. Yeah, I'd say if there was anything that at least personally I enjoyed the most, it was like writing infrastructure as code for the first time. I had an interest in the past, but actually, writing stuff with what's called the Cloud Development Kit for AWS, and writing code that you could then see deployed into, production environment. In this case, one of the things was the state machine that we built. It was like a sort of a serverless thing with step functions, and essentially define all the logic and code, deploy it, and then you have it hosted on an AWS account. And I think seeing that process was pretty cool. But yeah.
Yeah, I could go. Of course, I had a lot of interesting experiences with the CDK and all the technical side, but I really liked working on a team of people who were really dedicated and enthusiastic about building something. Like in the past, I haven't had that experience a lot, so this is a very refreshing and also very satisfying experience for me, just to be with these two guys in Capstone.
And then I'll give an answer, and then we have a couple more questions incoming in after. So yeah, for me, I really liked working on the webhook part of setting up like the webhook and interacting with the GitHub API. And one of the big reasons is it seemed so intimidating, and it kind of felt kind of impossible at first. And then fortunately, like we have Capstone mentors, and like our mentor really kind of gave me the confidence to take a look at it and to just kind of read about the API and see what I can do. And it gave me like a lot of confidence to do that. So I really like kind of appreciated that that extra like motivation that I needed. So we got a couple more questions. This next one, can you talk about the scaling that Fargate allows?
Yeah, we use the AWS Cloud Development Kit, or CDK, to spin up and provision all the infrastructure. And specifically for the backend service, we're using the higher level construct called Application Load Balance Fargate Service from the AWS EC Patterns library. And this creates the cluster as well as a load balancer. However, you need to specifically specify the metrics that it observes and uses to perform the scaling. And so on that construct, you can define a property called the auto scale task count, set the minimum capacity and maximum capacity, which basically means how many containers you want at least and how many containers you want at most. And as far as the metrics, you can use different ones like CPU, memory. For us, we use requests per target as a metric. We set it to 1,000 requests. And then if it exceeds that, it's going to add additional clusters to handle the load. We've also set scaling in and scaling out cooldown durations, which are 1 minute. So it can scale in a gradual way and not leave users hanging.
Okay, thanks, Jason. We have another technical question that I think Ethan's going to take here, and then after a couple more general ones. So first, if a pipeline builds multiple microservices, how do you specify the control of whether to continue if one microservice fails?
Yeah, that's a good question. So the way Seamless actually works in terms of building microservices is the microservice deployments are like entirely decoupled from one another. So essentially we have, this one-to-one attachment between CI/CD pipelines and the microservices. So if you run a CI/CD pipeline for one of those microservices, it doesn't say redeploy the entire infrastructure. It just redeploys that specific microservice. There's a way to do that in Fargate with like a force new deployment option, the CDK that we played around with. So say if like that one microservice fails when it's building, it will just never make it to deployment, but the entire production environment will just stay in the same state. So yeah, I hope that answers your question, Jenny.
Okay, we have another question. Probably, I think Jason could probably take this one. Could you explain a bit more about running a Docker container inside of a container? How would you configure the environment for the container that runs a task?
Yeah, I'm really glad you asked this question because it's something that we struggled with a lot. And so as you've correctly observed, everything runs in Docker container, and sometimes we need to do Docker build inside of those containers. And so there are two options we explored. The first one is what we call, what I would call true Docker in Docker. And there is an image on Docker Hub called D&D, which has Docker daemon installed inside of a Docker container. And so what you can do with that is have a parent-child relationship where you have a child container running in a parent container. However, the downside to that is security. To have that sort of scenario, you need to run that parent container in privilege mode, meaning that it has full access to the host. And so it's not a good idea. So after some more research and reading the blogs from some of the Docker developers, there is a second approach, meaning if you don't actually need this real parent-child relationship, and all you need is to just run Docker build or some other sort of Docker push, other Docker commands, then you don't have to expose the system to those sorts of security vulnerabilities. You can do something which is a bind mount. So I'll go into this a little bit. So when you have the Docker engine running on your virtual machine, it runs a Docker daemon or service, and that binds to the Unix socket on the host machine. Going one level of inception deeper, when you have the container, it also has Docker daemon installed and also has its Unix socket. And so what you can do is bind the internal container's Unix socket to the parent container's Docker Unix socket. And you're basically, the child is using the parent's Docker daemon in order to do Docker stuff. And so it goes from a parent-child relationship to kind of a sibling-sibling relationship. So our task container is performing work aside itself, not inside itself. I hope that answers the question.
Thanks, Jason. So we have one more question, I guess I'll take, and then we'll close it after. So this is from an anonymous attendee, and it says Team Serjon or Team Rodney asking for a friend. And so this, of course, refers to the famous rivalry in launch school. And like having been in Capstone, we've had a lot of great help from both Serjon and Rodney, Serjon in data structures and algorithms, and Rodney's been our team mentor. And for having been our team mentor and worked with us so much, I guess Seamless has to be within the Team Rodney camp. And yep, so thanks to everyone, and I guess we'll close it out there.